So in the last class, we have seen the steady state error and what is the purpose of finding steady state error and expression for steady state error and what are the static error constants. Okay. So similarly, that is mainly depends upon the type of the steady state error mainly depends upon the type of the input and also the type number of the system. So we have obtained expression for error signal, and from that, so when the input is unit step input, so we have already obtained the steady state error for the system given. So which is, so this is the expression steady state error when the input is unit step signal. Maybe any type of that is mainly depends, steady state error mainly depends upon the type number of the system and also it mainly depends upon the type of the input. Here, so we have applied different. First case we are going to apply different types of input signals. So that means instead of RS, so if we substitute 1 by S, and so you will get the steady state error as 1 by 1 plus Kp. So where Kp is equal to limit S tends to 0, G of S, H of S. Okay, this term is called as position error constant. Okay, so this is static error constant. This one is when the input is unit step signal. So Kp becomes the position error constant where Kp is equal to limit S tends to 0, G of S into H of S. Okay, this part I think we have completed in the last class. So that is mainly depends upon the type number of the system. So type number means we have already discussed, that is the number of poles present at the origin. So in this case, if we observe the type 0 system means in the denominator there is no S term. So if S is present means that is the type becomes whatever be the power of S, that means the poles present at the origin, that becomes the type of the system. Type number of the system. Here for a type 0 system there is no S terms in the denominator. Okay, or no poles present at the origin. So that's why the expression G of S into H of S, this is called as loop transfer function. Okay, in the loop transfer function, there is no S term in the denominator. So it is, even if we substitute S is equal to 0 in the given expression, so you will get a constant value. So steady state error is some constant, 1 by 1 plus Kp, it is some constant. So entire steady state error becomes a constant value. Okay. So for type 0 system, when input is unit step input, steady state error is constant value. That means it is not reaching to the desired input or desired response, desired value. Okay. So for type 1 system, if we observe, so type 1 system means one pole is present at the origin. So that's why the loop transfer function we can represent it as in this fashion, limit S tends to 0, K into, so number of zeros, number of poles, and in the denominator we have one S term. One pole is present at the origin, that's why it is called as type 1 system. Okay, in that case, if we substitute S is equal to 0, this entire thing is constant, whereas because of this S present in the denominator, the value becomes infinity. So infinity means if we substitute infinity in Kp in this position, so you will get 0. Steady state error is 0 means there is no steady state error. That means it is reached 100%. Okay, the desired value. So for higher order systems, even though if we consider a type 2 system, type 3 system, any type of system for higher order systems, when the input is unit step, Okay, so if we calculate steady state error, that is 0. Only for type 0 system we have some constant value. Okay, so that we have to write in this system type 1 or above. For a unit step input, kp value is infinity, hence the steady state error becomes 0. This is very important note. Okay, so now the second input, if we consider a unit ramp input for the same system, so if we consider a ramp input, the steady state error becomes limit s tends to 0. This is a known formula. Limit s tends to 0, s into r of s by 1 plus g of s into h of s. So this is error signal. So uh, the steady state error becomes when the input is 1 by s square. So because a ramp input means its Laplace transform is 1 by s square. So simply substitute in this and find out the steady state error. So the expression is going to be 1 by. So here if we substitute s is equal to 0, this term becomes 0. Only the term remains. That is 1 by limit s tends to 0, s into g of s, h of s. Okay. One bit g of s into h of s. Okay. So that is so are you able to see my screen? Okay. Okay. So limit so you will get 1 by limit s tends to 0, s into g of s into h of s. This is called as velocity error constant. So velocity error constant is represented by we simply to calculate steady state error, the first we have to calculate this error constant. Once we get the error constant, we can directly say about steady state error. So error constant for position error constant, kp is g of s into limit s tends to 0. This is kp. So kp, that is limit s tends to 0, g of s into h of s. So this is position error constant. Velocity error constant means limit s tends to 0, s into g of s into h of s. Only the difference is s. Okay. So velocity error constant is when the input is unit ramp input. So simply limit s tends to 0, s into g of s into h of s. This is called as velocity error constant. So for a type 1 system, if we calculate velocity error constant, that is equals to 0. Because type 0 system, there is no s in the denominator, only the s present in the numerator. Because of this s, the remaining terms will give a constant value. Because of this s, substitute s is equal to 0, s into constant, you will get a 0 value. This kv, that is velocity error constant, is 0. Therefore, the steady state error becomes infinity. So when input is unit ramp input, velocity error constant is 0, whereas the steady state error becomes infinity. Okay, so steady state error becomes infinity means it is an uncontrolled system, strictly speaking. We cannot control its value is infinity when the input is a unit, a ramp input for a type 0 system. The error constant becomes infinity error. Okay, the error constant is 0, steady state error is infinity. Please note all this. Velocity error constant. Okay. Okay. For a type 1 system, apply the same to type 1 system. Type 1 system means you will have s in the denominator. One pole is present at the origin. So s is present at the denominator. Because of this, s and s gets cancelled. Okay. So you will get a constant value here. Velocity error constant is some constant value. So steady state error becomes a constant. 1 by constant, you will get some constant value. For type 1 system, steady state error is 1 by kV. Okay, it is a constant value. So if we consider for type 2 system means s to the power of 2. You know, in the denominator, s square term is present. S square term is present in the denominator. So 1s gets cancelled. Because of this s, if we substitute 0, this velocity error constant becomes infinity. So steady state error becomes 0. So for type 2 system. Okay. So for higher order systems more than type 1, so the steady state error becomes 0 when the input is unit ramp input. So this is the system we considered. So type 1 and type 2. So type 1 system, when the input is unit ramp, there will be a constant steady state error. For a type 2 system, and above, when the input is unit ramp, the value of kV, that is velocity error constant, is infinity, whereas the steady state error becomes 0. Okay. So no need to write down all this, simply calculate kV, write down kV, and just similarly for the type 2 systems, write down this conclusion. Are you able to follow? If you have any doubts, you can raise. Raise your doubts. Okay. Now coming to third input, that is unit parabolic signal or parabolic input. So parabolic input, the Laplace transform of unit parabolic input is 1 by s cube. So R of s, if we directly substitute R of s is equal to 1 by s cube. So here 1 by s cube, this is steady state error becomes, so 1 by s cube, limit s tends to 0. So here substitute instead of R of s 1 by s cube. In the denominator, if we simplify that one, so s square, in the denominator 1 by s square, if we simply multiply with this, s square into s square, s square plus s square into g of s into h of s. So if we substitute s is equal to 0, this term becomes 0, only the remaining term is this one. So this is called as acceleration error constant, Ka. Ka is acceleration error constant, where Kv previously when the input is unit ramp input, that is velocity error constant. When the unit step input, for the unit step input, we have position error constant. So position error constant means limit s tends to 0. So g of s into h of s, this is loop transfer function. So here it is limit s tends to 0, s into g of s into h of s. So for position acceleration error constant, but it is s square into g of s into h of s. Okay, this we have to remember. These are called static error constants. Okay, so whereas the acceleration error constant becomes limit s tends to 0, s square into g of s into h of s. So this is called as an acceleration error constant. So if we test for type 1 system, so for type 0 system, it is also, you will get the same answer. So for type 1 system, so if we observe, that means type 1 means denominator, one pole is present in the denominator. So this s and s gets cancelled. If we substitute s is equal to 0 here, you will get 0. Acceleration error constant is 0. whereas the steady state error becomes infinity. Similarly, for type 0 system, so type 0 system, that means limit s tends to 0. Here it is s square into some constant value. Okay, there is no s term present at the origin. You will get some constant value. This is constant. So if I substitute s is equal to 0, again you will get 0 value. The acceleration error constant for type 0 system and type 1 system, it is 0. So therefore, the steady state error becomes infinity. Just note down this. So for type 1 system means same expression we have to consider. Okay. Next, coming to type 2 system and type 3 systems. So for type 2 system, type 2 system means again in the same explanation. So this is type 2 system. Two poles are present at the origin. So because of this term, s square present in the denominator, so these two gets cancelled. So you will get a constant value. So steady state error becomes constant. Acceleration error constant is constant. Steady state error is also a constant value. Okay. Next, coming to higher order systems, that is 3 and above. So because of this term, this is third type 3 system. So this is gets cancelled. You will have one term, that is one s term in the denominator. So if we substitute s is equal to 0, acceleration error constant becomes infinity, whereas the steady state error becomes 0. For type 3 system and above, the parabolic input, the acceleration error constant is infinity. Therefore, the steady state error becomes 0. Okay. Now, if we consolidate all these, so you get this table. This table is very important. In case of competitive examinations, also you will get one question from this error constants. Definitely, you will get one question in any competitive examination. Maybe an RRB examination or railways examinations or any gate examinations. So based on error constant, steady state error, you will get one question from this topic. Okay. Any NTPC examinations or any examination. Any competitive examination, either Genco, Transco, Discom. So definitely you will get minimum one question. So these are the steady state error for various types of input. If we take, if we calculate the first, we'll see this table. Steady state error constants for various types of systems. So type 0 system, type 1 system, type 2 and type 3 system. If we calculate the error constant, position error constant is constant value for type 0 system. We have already derived. For type 0 system, position error constant is constant value. Okay. So for type 1 system and higher order systems, we have infinity. Okay. So velocity error constant is 0 for type 0 system, whereas type 0 system, so velocity error constant means when the input is unit ramp input. Acceleration error constant means when the input is parabolic input. So these are the constant values. If we tabulate the previous derivations, you will get these are the error constants. So the corresponding steady state errors, if we take for type 0 system, so here error constant is Kp value is constant. So this value is also a constant. You will get a constant value. So because Kp value is infinity for type 1 system, so here that becomes 0. 1 by 1 plus Kp. If we substitute here infinity value, you will get 0. So for if I observe the steady state errors, when the input is unit step input, the steady state error is 0 for first type 1 and above systems. Okay, type 1 and above systems we have 0 steady state error. So when the input is unit ramp input, the steady state error is 0 for type 2 and above systems. Okay, for parabolic input, when the input is parabolic, the steady state error is 0 for systems type 3 and above, and so on. Okay, so these static error constants are mainly defined for standard inputs. Standard inputs means unit step, unit ramp, and parabolic inputs. Only 3 inputs. Okay, so static error constants are defined for unit step input, unit ramp input, and unit parabolic input. Okay. So just note down this table. So up to this, these are nothing but transient or time domain specifications. What are time domain specifications? Rise time, time domain specification, rise time, peak time, peak overshoot, and settling time, steady state error. These are the time domain specifications. Based on this specifications, we can define a response. Okay, these are, so just based on these specifications, we can judge how the response is going to be, whether it is a stable one or unstable one, or whether it is more stable when compared to other stable systems. Anything can be defined, anything can be explained using these specifications. Okay, so next we'll do some examples based on the formulas derived in the previous sessions. Okay, let us take one example. Can anybody tell This is the given. Determine the type and the order of the systems. So given the system transfer function is g of s into h of s is equal to k by s plus 1 s plus 3 whole divided by s square plus s plus 2 into s plus 5. First one, if I observe the first one, so for first case, type of the system means the number of poles present at the origin gives the type number of the system. Here the two poles, these are called poles. Roots of the denominator polynomial are called as poles. Okay, so poles present at the origin at this or origin s is equal to 0. So we have 2. So this is called as type 2 system. Whereas for this, for second case, type number is 1. One pole is present at the origin. That's why it is called as 1. Okay. For third case, there is no pole present at the origin. So type is simply 0 type. There is no pole present at the origin s to the power of 0. That is constant value. Okay. So we can write it as type 0 system. Whereas for the fourth one, total 3 poles present at the origin. So type number is 3. Simply by observing the number of poles present at the origin in the given transfer function, we can say the system type, whether it is type 0, type 1, type 2 or type 3. Okay. So coming to order. Order means, so the maximum value of s. Okay, power of s, not value. So it's power of s. In this expression, if we simplify this one, that is fourth order. The denominator polynomial is of fourth order polynomial. In this case, the second case, it is also a fourth order. Okay. Yes, yes, yes. If we multiply, you will get s to the power of 4. So in this case, you will have s to the power of 7. The maximum s to the power of s is 7. So here the maximum power is s. So this is fourth order system. This is also a fourth order system. Here it is second order system. Whereas in this case that becomes a seventh order system. So like that we can define order and type of the system. Okay. Simply note down. The open loop transfer function has 2 poles at the origin in first case. So it has type 2 system. The highest power of s present in the denominator is 4. So it is called fourth order system. First case, second case, third case and fourth case. Type 2, type 1, type 0, type 3. Okay. These are the answers. If your mic. If you have any doubts, you can raise. Okay. So I think you can write type number and order of the systems. Note down one more example. So here it is the example. So a unity feedback control system has an open loop transfer function g of s is equal to s by 5 by s into s plus 1. So open loop transfer function. Okay, unity feedback. So here unity feedback means simply h of s is equal to 0. H of s is equal to unit value, sorry. H of s is equal to unit value. So find the rise time, percentage overshoot, peak time, resettling time for units for step inputs of 10 units. Okay, step input of 10 units. Here the amplitude is 10 multiplied with unit value. Okay, first calculate for unit value. If necessary, that is multiplied. The answer can be multiplied with 10. Okay, if necessary. Okay, and also determine the peak overshoot. The percentage overshoot and also the peak overshoot. Okay. So now, first step we have to find out the closed loop transfer function. This is given open loop transfer function. Finally, so C of s by R of s is equal to closed loop transfer function. So closed loop transfer function means simply, so here it is g of s by 1 plus g of s into h of s, where h of s is equal to unit value. That's why it is not given. So C of s by R of s, the closed loop transfer function. CLFTF, closed loop transfer function is equal to C of s by R of s is equal to g of s by 1 plus g of s into h of s. So simply substitute and simplify, you will get an expression like this. 5 by s square plus s into s plus 5, s plus 5. This is our closed loop transfer function. Now, our standard form of closed loop transfer function. Okay, so standard form of closed loop transfer function. This is a second order system. Okay, so it is the standard form omega n square by s square plus 2 zeta omega n s plus omega n square. This is very, very important. We have to remember this one. Closed loop, standard form of closed loop second order system. So it is omega n square by s square plus 2 zeta omega n s plus omega n square. Compare this with the closed loop transfer function of this system. So if we compare directly, so compare the denominators. So omega n square is equal to 5. Omega n square is equal to 5. Omega n is equal to root 5. Its value is 2.236 radians per second. So if we compare S coefficients, so S coefficient in this case is unit value. That means 2 zeta omega n is equal to unit value. Once we have omega n value, simply substitute and find out zeta. First, we have to find out zeta and omega n. Then only we can find out rise time, peak overshoot. Everything is in terms of zeta and omega n. If omega n and zeta directly that is given, no need to find out this closed loop transfer function at all. Directly we can substitute the values in the given expressions. Okay. Note down. Okay. So next. So here I have equated this 2 zeta omega n, that is S coefficient. Comparing S coefficients, you will get 2 zeta omega n is equal to 1. So zeta is equal to 0.223. This is an underdamped system. Since zeta value is lying in between 0 to 1, that is called as underdamped system. Okay, so we can easily say the response of this system. This is underdamped response of the system. We can also find out omega d using the expression omega n is equal to under square root of 1 minus zeta n zeta square. So we'll get damped natural frequency. Omega d is damped natural frequency, where omega n is called as undamped natural frequency. Okay, we can find out omega d value. So, and also theta value, theta is equals to tan inverse of using the right angle triangle. So this is theta 1 minus zeta square zeta, and this is unit value. So from this we can find out theta in terms of radians. Radians per radians, theta is in radians. Okay, just a minute, please note down. Okay, so now we have here units for this is radians, not radians per second, it is simply radians. Okay, rise time we have formula pi minus theta by omega d. So pi value 3.14 radians. Okay, so whereas theta we have already obtained. So theta, so if we simply substitute in this formula, in this expression, we will get rise time is equal to 0.845 seconds. Okay, so similarly the percentage overshoot. So we have percentage overshoot is equal to e to the power of, simply just a minute, note of this. Okay, just this is the percentage overshoot. So percentage overshoot is, it comes around 47.8%. Simply substitute the values, and if we calculate, that becomes 47.8%. The peak overshoot value is going to be 0.478 for the inputs of 10 units, because that is 10 units input. the peak overshoot becomes, if I just multiply with 10, that is 4 into 4.78. So here is a note: rise time, peak time, peak overshoot, percentage overshoot, and settling time remains the same for input as well as step input for any amplitude. So there is no change in, even though if we observe the formulas or if we calculate the formulas for different amplitudes, you will get the same value, but only the peak value varies. So percentage peak overshoot, okay, percentage peak overshoot remains the same, but here the peak overshoot value changes. That is, the peak overshoot of unit step is 10 times the peak overshoot of, that is 10 units is 10 times the peak overshoot of unit step. Only the peak overshoot value changes. Percentage overshoot and all the other rise time, peak time, everything remains the same. Okay, is it clear? Okay, now coming to peak time. So peak time is pi by omega d. So we can find out Tp is equal to pi by omega d, which is equal to pi by 2.124. Okay, the time constant value, that is 1 by 2 zeta omega n, which is equal to 2 seconds. For 5% error, it is 3 time constant. For 2% error, it is 4 time constants. You can find out the settling time, so which comes around 6 seconds and 8 seconds. The formulas are very important formulas. These formulas, settling time, peak time, everything. If you have any doubts, you can write. Otherwise, we will stop here. We'll continue in the next session. Any doubts regarding today's class or previous classes? You can ask. Any doubts?